now that we've mentioned the key inequalities, I want to explain what kind of a key observation that allow okay, I'm going to show you where all the hard math is buried in this Newton above Hodge business. Okay, so we have this Newton above Hodge business, and we had this system of inequalities here. We had these ugly inequalities, and these ugly inequalities are what allow us to detect when one polygon is going to be above another polygon. Okay, and so it turns out, okay, so that if we have a crystal, so here's the key observation. This is what's going to get things moving. So suppose we have a crystal, or let's say a span with Hodge numbers, EI. Okay. Then it turns out that the length of an R module of this M prime modulo, so we're going to take this to be injective here, so we're going to view it as a submodule of a p to the m here intersected with m prime. So this thing is actually going to be equal to m e0 plus m minus 1 e1 plus etc. so on and so forth to e to the m minus 1. Okay, how do we see this? So why is this just an observation and not a theorem? Well, it's really easy. So this thing is here. This is just okay. So since you're modding out by p to the m, so this is the 0th piece. So this is going to be like here. This is going to be contributed from a factor of r minus p to the m to the e0. Okay. So we're going to have a bunch of different parts. So and then here you're going to have r to the p minus 1. And so on and so forth. So this is kind of which each of these factors mean. So the m corresponds to this r to the p to the m, and then this part here, and then we're going to have, since it's e0 dimensional, this piece, you're going to have that many of them. Okay, and then you go on and do this for each of the pieces. So again, this goes back to this very basic fact about that each R span has a direct sum decomposition like so. Okay, and then into these free, so again, they're free R modules, they're finite rank. There's nothing complicated about this. Okay, then after this key observation, there's going to be there's this key inequality that the key inequality is the following. So the key inequality from which everything else will essentially follow is that this length as an R module of m prime mod p to the n m intersect m prime. This is a very special case when m prime is equal to this the crystalline for some jth crystalline of the Frobenius twist over K. And so we have this, we're given this crystal. So we have this crystal, and we can take the associated span. And it turns out that we're going to have this inequality in this special case. Okay, so x over k is smooth. So this is where all our hypotheses are really used. This is smooth and it's liftable. Then to mod p, then this is going to be m h0 plus m minus 1 h1 plus so on and so forth h to the m minus 1. Here h, let's say I, is going to be h j minus I j here of x over k. Okay, so these are these Hodge numbers. So these are the Hodge numbers. Okay, that's what's important, is the comparison here. Okay, the proof. So the proof, you're gonna find something to surject onto here, and that's going to be involved. and you're going to use a Cartier operator argument, and you're going to kind of use the fact that you have something that's rejecting on here to estimate length. So that I'm just not going to say any more about that until I maybe if I do prove this in a video, I'm going to link to it. Okay, so this is the hard part. This is the hard part of the theorem of Newton above Hodge. Okay. And so what does this actually give us? So this thing here is the crystalline Hodge. This is the crystalline Hodge numbers. Okay, from here. This is what we had. So we had this crystal, right? And the crystal, so we can, for any crystal, we can do this. In particular, when we have the crystal associated to crystalline cohomology, we'll be able to compare it to the actual Hodge numbers. So the crystalline Hodge numbers will be rated to the Hodge numbers. And so where does this go? Let's go back to here. Okay, and this is this inequality here. Okay, this inequality is going to be a consequence of linear algebra essentially. Okay, so this is the hard part. This part here is linear algebra, and I'm going to explain this. Okay, so recall that we could compute. So I want to prove the second part. Let's say I'm gonna prove. So this is a proof of the Newton of the crystal is above the Hodge of crystal. Okay, but the Hodge of the variety and the Hodge of the crystalline Hodge and the actual Hodge is the difficult part. Okay, so this is what I'm going to prove. Okay, that's kind of a semicolon there. And what I want to do is so let EI or EX be the Hodge polygon. Polygon of a crystal, of a span or crystal, whatever. Okay. Okay. So what we saw is that we computed of a span, let's say T. Okay. Let's say from M prime to N. Okay. And what we did is we computed previously, or I told you, the index of the first non-zero Hodge number of the wedge power of this crystal. Okay, so the first non-zero wedge power of a crystal, and what was it? It was okay. So it's this crazy thing. So let me go back here. So you just linear algebra for okay, so we had this formula. It said that the first non-zero index of first non-zero Hodge number of lambda I of t. So this was equal to this sum, this ugly sum. Sorry, E1 plus 2E2 plus J minus 1 EJ minus 1 plus j times I minus e0 plus ej minus 1, where I was in this interval, the j minus first interval and the jth interval. Okay, so we had this. Okay, it also turns out that there's kind of some elementary computation that we can see is that that from the fact that okay, we had this. We also had that. So I'm going to make a claim. The trace of lambda I of t is equal to -1 to the I of ai. Okay, and where the characteristic polynomial of t is equal to a0 plus a1, let's say x plus an x to the n. Okay, so this is the characteristic polynomial of this. Let me explain why this is true. So this is just comes from this description. If you have a map from V to W, then you can take some power of it, T I of V to I of W, and you have these guys, wedge VI 1 VI. And and here, in particular, if you have an eigenvalue, or if you have a bunch of eigenvalues, you can see that the eigenvalues are going to the wedges of eigenvalues are eigenvalues. So since wedges of eigenvalues are eigenvalues, or sorry, wedges of eigenvectors are eigenvectors. The point spectrum of the eigenvalues of something like a wedge power of t will be equal to the products of t products of these guys. So times. So this is t sigma p of t, and so this is going to be I times. And so this thing will contain these products of eigenvalues. Let's say j0, j1 up to lambda of ji. So it'll take like products of these guys, and if you take products of these guys, right, you can see that. So as you recall that x minus a bunch of things like this will be a sum of symmetric polynomials. So elementary symmetric polynomials here, j, let's say xj, and then we have this -1 to the j factor, like so. J is equal to 0 up to the number of these. And here, this is the elementary symmetric polynomials. Polynomials in lambda i's. Okay, and so then if this tells us that this combination here of -1 to the j. So after I get rid of these things, sorry, this thing here. Well, this is going to be n choose j terms, right? And it's going to be the sums of lambda I 1, lambda ij. Okay, so I kind of switched notations twice. Whatever. Okay. Okay, so this tells us then that this explains this part here, and hence this claim that that the trace of this wedge power of an operator is going to be some alternating sum of the characteristic polynomial. So, sorry, alternating part of it's almost this elementary symmetric polynomial. So you just have to account for that normalization factor. Not normalization factor, but the -1 up to a sign. Ugh, that was bad. Okay, so now where were we? So we were with we wanted to show that that the crystalline Hodge is above the other Hodge. Okay, so now we have the first non-zero. We have the index of the first non-zero Hodge number. We have this thing here, and now we can use the alternative description of the Hodge polygon. Okay, so the alternative description of the description of the Newton polygon plus the fact that this p to the ei divides. So this is the index of the first non-zero Hodge number of -1 to the ai. So this is going to be true. So yeah, the other thing to notice is that this thing here is equal to ei. Right? So this is actually the function of the this is the Hodge polynomial, or the Hodge polygon at I. So this is a kind of the miraculous part, is that this is the Hodge polygon at I. So we can use that. So this is the Hodge polygon at I, and this tells us that this is above this. Okay, so the Hodge polygon, this part here, so the order of AI is bigger than or equal to EI. And this is equal to, this is above this is the Newton polygon here. So because this is the convex hull, so this is determined by the convex hull of these i's and then the orders of these ai's. Okay, and this was the alternative description of the Newton polygon. Okay, so we had this divisibility. This told us that here, this is strictly above here. Well, now we may have like some points, okay? And what we do is we just take this polygon above the convex hull of these points. So these points that I drew here, these are the points AI, the order of P of AI, and that's what we have. Okay, so this shows us that so this is the Newton polygon of the crystal is above the Hodge polygon of the crystal, and that's how the proof goes. That's the easy part. That being said, I'm gonna bring this video to a close. Thanks for watching. I will probably clean up some of the parts of this video that I don't like. So there'll be some in and out. Oh, I don't know. I don't need to say that.